Perfect. Okay. So, hi everyone. I'm Luke Antigan, CTO at Lightning AI. Lightning AI is the company behind PyTorch Lightning that some of you may know. And we'll go through some of the new things that we're introducing and some themes around training distributed with Lightning. All right. So, I'm focusing on foundation models because it's something that is bringing up a lot of need for distributed training and a foundation model. Well, Wikipedia definition is a large model trained on a vast quantity of unlabeled data, scaled, resulting in something that you can use to do other tasks that are not necessarily related to the loss that you use during training. And PyTorch Lightning has been used to train several foundation models successfully. I would say the most common thing to tell is that PyTorch Lightning was used to train Stable Diffusion that many people know, and both the original repository, Compass repository, and the new Stability AI repository used PyTorch Lightning extensively, and the training has been conducted using PyTorch Lightning. But also other projects that are very large scale models that had been used, for example, in the scientific world, like OpenFold, which is a reproduction of AlphaFold 2, is based on PyTorch Lightning for its training. And the new NeMo Megatron and the Megatron platform that NVIDIA is presenting is all powered by PyTorch Lightning. So what is PyTorch Lightning about? It's about trying to make people focus on the science rather than with the engineering hurdles as much as possible. And the concept of boilerplate is dear to us. Boilerplate is code that you need to write because it needs to be there, but you, as a scientist, don't necessarily understand it fully or control it fully. And it's a place where a lot of bugs and hidden gotchas can hide. And so we try to abstract that out of users' code so users can express their intentions, and then we take over the engineering part. The PyTorch Lightning project is very widespread use. I think the stars now have increased since I took this screenshot. We have a ton of downloads, monthly downloads, and there are many projects using Lightning and many companies using that around the world. So what is Lightning for the ones of you who have not seen it? I would show some screenshots of code. We won't do code heavy stuff, but just to give you the main view from a mile high is PyTorch Lightning is not a wrapper around PyTorch per se. You still write pure PyTorch, but it's a way to organize your PyTorch code. And the two main abstractions are the Lightning module, where you write the model itself in PyTorch. And then you also define how the training step happens and what optimizers you are using. And then there's a number of other hooks that you can optionally override. And the process is really to take raw PyTorch code and decompose it into pieces and override each hook with the parts of the code that express exactly what happens in that life cycle element. And so we through this specification, which is almost a standardization on how deep learning code is written, then we can pass it to the trainer, which is the main element that drives the training. And since you broke up the training code for us, then we can take all the pieces knowing what should happen in each piece, and we can manage the training loops for you. And this means that whatever you write in the Lightning module will be valid if you're training locally, if you're training distributed, and so on. And we take care of everything else. And by doing so, you have access to trainer switches that just by flipping that switch, you can get from one device to another, one accelerator to another, distribute on multiple devices, use distributed strategies that you can configure and pass or just specify through the string, change the precision, use callbacks. And the advantage of using callbacks, like I want to use stochastic weight averaging, or I want to checkpoint or terminate my training when the loss reaches a certain level, and so on. All these things become something that a company or a group of people can share and use in all their their projects. It becomes a way to reuse and share knowledge. So what happens when you call trainer.fit? Sorry, I'm going back here. At the bottom, you say trainer, you instantiate the trainer, we specify some trainer flags, and then we call trainer.fit and we pass the model that is basically the instantiation of this class here that specifies the model and the trainer step and the optimizer. So what happens when you call fit? So the anatomy of fit is the following. This is not what the user is supposed to write. This is rather what happens behind the scenes, like at a high level. There are certain things that notify the trainer that certain things are happening, and then there's an iteration over epochs. We go into a fit loop. There's some device configuration before that. And then in the fit loop, there's some life cycle moments again. And then for each batch from the data loader, there's data transferring to the device. Then the training step is executed. And this is what the user basically implemented in the Lightning module. And then there's some operation with zeroing out gradients, computing the backward, and you find a lot of like hooks being on before, on after. These are all events that are generating through the training that you can hook your own code into. So whenever this happens, then you also have control and can execute code at this precise moment in the training loop. And then there's a call to optimizer step, and the train batch ends, and so on. And optionally, there's a validation loop. So this is the standard kind of life cycle of a call to fit. And so you can really think about something like as PyTorch Lightning as something like this. You have a trainer that is kind of opaque to you, where you can plug model, accelerator, callbacks, strategies, and then the model is something you write, and all these things are things that you write, and the trainer is really just a runner of all these things, an orchestrator of all these things. And this is important, of course. If you have a small repo, you're driving your project solo, you're on your own workstation. This is not that big of a deal if you really know what you're doing. But the moment you're scaling up, the moment you work as a team, then having a Lightning module as an abstraction, for example, and this is something we noticed, that a lot of people are adopting PyTorch Lightning because it provides structure to the code. And you can really see that teams standardize across these abstractions, and the code written by a person becomes readable by another person, which is not exactly always the case when you look at research code, especially when the researchers are kind of software development mindset, and they tend to write their own abstraction, one abstraction per person. And I've seen it happen in many teams. So this is a way to work together on a common code base, and callbacks and strategies are ways also to provide standardization across certain functionalities. Of course, stop me whenever I'm going to go on, but you're welcome to ask any questions at any time. So as I was mentioning, Lightning module is where the flexibility and collaboration is, and the trainer is for whatever is abstracted away and that we consider boilerplate. So you focus on the science and we do the engineering. This doesn't mean that you cannot scale up. Actually, this allows you to scale up because the Lightning module stays kind of the same, and the trainer can acquire new different strategies and different ways to scale out and distribute your computation. So, for example, here you can see how you can leverage, and we will look into those in a few minutes. Strategies to kind of scale out your training just by changing one flag or configuring having some configuration on the trainer. However, in the age of foundation models, sometimes the science is the engineering, in the sense that when you have a very long project, very large models, every little iteration on the model, sorry, every little change on the way you train impacts your efficiency during training. And so sometimes you want full control on the training process, and you don't iterate on the model that much. So PyTorch Lightning is ideal, especially when your main focus of iteration is the model and the training step, the optimizer, and so on. So more the science part of it. And you don't care that much about what happens in the trainer, except if you're writing a strategy, and it's fine. But if you're writing a strategy, you need to understand how the trainer works. So in that sense, you need to commit to understand how the trainer works. Sometimes you just need to train your large model. You want full control. And so we wanted to also provide full control to users without having them to learn how the trainer works internally. And so adopting PyTorch Lightning or raw PyTorch was a binary choice until, well, not today, but 15 days ago. And because with raw PyTorch, you had full control, you had to write a bit more boilerplate because everything is up to you. Also, configuration of distributed stuff is up to you. There are many subtle things that you need to get right there. But if you do, you have full control. And the binary choice on the other side was fully managed. Less boilerplate, but if you want to understand exactly what happens at a certain point, you need to dive into what the trainer does. And it's not always easy to do so. And so with Lightning 2.0 that we released 3 weeks ago at this point, we introduced a gradient between raw PyTorch and PyTorch Lightning under the form of Fabric. And Fabric, you can think about Fabric as we called it at the beginning, we called it Lightning Unbundled, in the sense that it basically ships many of the internals of the PyTorch Lightning trainer as building blocks that you can use in a raw PyTorch code base to augment it. And the amount at which you actually augment it, so the amount of managed things that you can have, is up to you. So we'll go through a bit Fabric a little bit to give an idea on what you can achieve with it. So take raw PyTorch code, and the first place you need to look into is, well, you add a construction of an object, which is the Fabric object. And the Fabric object will manage some of the things that you will see right now, but essentially it's where I can plug a number of things, like for what accelerators I'm using, what precision I want to run my code at, and what distributed strategies I'm using. And then I instantiate the objects just like I would do in standard PyTorch code. So I instantiate my model, my optimizer, and so on. And then I just pass them into setup methods in Fabric, and Fabric kind of augments them. For example, if I told Fabric that I want to run my whole code on TPUs, then that's the moment where the model will know about that, essentially. And then I can just run the training loop, and this train is written by me. So I have the for loops, I have everything just like in raw PyTorch code. So it's usually a 5 to 10 lines change to turn raw PyTorch code into Fabric. And so instead of an opaque training loop, right now you have something that you can actually write and control, and then but you can still have things like loggers, accelerators, and strategies to plug in into your custom loops so that you can actually augment it and have some of the advantages that you have in PyTorch Lightning in terms of factoring out some of the aspects that are more gnarly sometimes, but still retain full control of what happens. And here is how you instantiate a Fabric object. You tell it how many devices you're running on, what kind of accelerator you're using, the strategy, is it a single device, is it DDP, FSDP, deep speed, and what precisions you want, like is it 16-bit, 16-bit mixed, and so on. This is an example on how you pass a logger. So you can pass n loggers to the Fabric object, and then when you in your code, whenever you call fabric.log, then it would log to these loggers. Why is this handy? Well, it is handy because this is the only thing that changes in the end. So your code becomes constant. It doesn't need to change when you change the way you log, except when instantiating the Fabric object. And so, how, if you do this job, you know how frequently machine learning code drifts because you need to use a different logger, different accelerators, and so on. And this is kind of convenient, a convenient way to take that problem out. This is how you save checkpoints. We have serial and distributed checkpoint support, so you don't need to worry about synchronizing in a distributed setting when you write out your checkpoints. We're adding support for native FSDP checkpoints as we speak. And so what we saw up until now is kind of raw Fabric, in the sense that it's really close to PyTorch plus a few things that Fabric takes care of, which is, again, accelerators, number of devices, and strategies, and so on. But you can do more with this. Like, if you really like your Lightning module structure is a way to standardize across your team, but you don't want to commit into the trainer, but you still want full control of the train loop, you can do that. You can have now your code within a Lightning module and have everything, all the things you had with your in the previous examples where we use the trainer, and instead use Fabric. And it looks like this. You have your own Lightning module with a training step, configure optimizer, and so on, so you can standardize around this. And now you can use it by instantiating Fabric, and then in this case, your model is a Lightning model. You set up your Lightning model the same way you would do previously, and then and then you can actually call the hooks, the training step, and so on manually, and a number of things will work. So the way you write the Lightning module is really similar, if not exactly the same, whether you use Lightning, PyTorch Lightning, or Fabric to run it. And so you can see that by doing so, your training code becomes kind of model independent, because it's all like life cycle moments and things are kind of delegated to the Lightning module. And this is a way to, again, minimize interdependencies in your code base. So this is another data point in the gradient, but then you can also use callbacks the same way you use them in the trainer, with the difference that now it's you who are calling the callbacks, or who are triggering the events, essentially. And so if there are multiple callbacks listening to this event and executing code as a result of this event having happened, then this will happen. And so basically, with callbacks and all this support, you can get to a point where you can build your own trainer, and we have documentation about that exactly. on how to build your own trainer. For example, we have people who are doing active learning or reinforcement learning, for which the trainer has always been a bit too stiff, that are now using Fabric to build their own reinforcement learning trainer so they can kind of standardize the way they train their models in that domain by using the Fabric primitives. So how do you scale out? You scale out by having more devices, having more nodes specified in the Fabric and trainer object. I want to stop here and ask for questions if there are any, otherwise we can continue.
So I have a question, Luca.
Yep.
So in your model, hi.
Hi.
I see in the Fabric function, you can specify different distributed training strategies. And I see you input the DDP, right? And can you support model parallelism also? Or are you leveraging some PyTorch distributed training libraries, or what's underlying it?
Yeah, so we are using, I will address it in a few slides, but essentially, right now we are supporting data parallel, sharded data parallel, deep speed. We don't have at this point any native support for model parallelism like pipeline. You need to implement it yourself, but it's doable with Fabric because you can use any primitives. We have some communication primitives that come with Fabric in the sense of like low-level collective calls, and yeah. So right now we're focusing more on the sharded data parallel story. But again, you can use tensor parallelism very easily with Fabric and also pipeline parallelism, since you're kind of in control uh, of the train loop.
See, wonderful. Thank you.
Thank you. All right, so let's see how Fabric and Trainer facilitate running on servers, each having a set of accelerators and uh, uh, communicating in between nodes. What you need to do is to start processes, right, using launchers running those scripts that will in turn launch multiple processes, one per accelerator. So we don't necessarily force you to run to have a launcher, but you can just run the Python script natively, which facilitates things when, for example, you are using a Slurm cluster, you have a Slurm launcher, and you just want to run your Python script, and this is what we do. But of course, you need to start one per node. And once that's done, then let's say we spawn or fork one process per accelerator, and there are a number of environment variables that usually you need to set, and you need to set them right. So we take kind of control over that. These are the environment variables we go after and we set for you. So there's a local rank, which is the rank of the accelerator on the machine. There's global rank, one unique identifier per accelerator, and then there's a node ID. And so once you launch Fabric in a network configuration, then you will have the variables available for you. And so if you want something to happen only on rank 0, you can just say if Fabric global rank equals 0. We also have support for collective groups for more advanced networking. For example, there's a group that is doing reinforcement learning, and they have different groups of machines communicating. So they have the agents and they have the optimizer nodes. and they want to keep those communications kind of siloed and independent, and they can easily do it with Fabric. And ways to scale out, of course, in the single node case, you have your data, you have your batch, you have your model, and then the memory that this model will need to run is roughly subdivided in these ways. You have the parameters, the activations, the gradients, and then a big chunk related to the optimizer state. Depending on the optimizer, of course, you will need to store one or more copies of the equivalent parameters. One way you can easily increase your batch size is by doing gradient accumulation, and there's an easy way to do that in Fabric as well, where you tell Fabric that you are accumulating, and so you're not zeroing out the gradients while you're taking the backward for each micro batch, and then at the intervals that you want, you will actually compute the backward step and compute the gradients. and call the optimizer step. So the backward step is called every time, but then the optimizer step is applied only after accumulating the gradients. And so this is a cheap way to increase your batch size. There are some strategies that allow you to do activation and gradient checkpointing. So you basically avoid storing activations using forward and only save a few of them in between the model to avoid recomputing too much. So it's not that you don't store any, you store an n of them throughout the model, and then you will recompute the ones that you need to recompute. So you trade some compute for memory, and this is what checkpointing does. We have support for mixed precision, where you can reduce the memory footprint by going through to a lower precision. And for some operation, full precision is automatically restored at computation time. And yeah, we support bfloat 16, float 16 Pro 32, which is what PyTorch supports, essentially. And then there are strategies that do offloading. For example, DeepSpeed does that, and we have full support of that, of course, where you, instead of sharding, you keep just a portion of the parameters, a slice of the parameters active, and then you offload the parts of the parameter that you are not using currently to CPU memory and just recall. Of course, you're trading off computation time for memory, latency for memory. And if this is not enough, of course, you need to spend more money and get another machine. And then you go on different processes, and of course, different processes have different devices, so you will have copies of the model. And in data parallelism that we touched briefly on before, the DDP strategy will essentially have separate instances of the distributed sampler, and then gradients will be synchronized across processes during the backward pass. So the two models are completely independent. They run on different data, but when it's time to apply the gradients to do the optimizer step, then the gradients are synchronized. So you make sure that the gradients that each model sees are the same, so the two sets of parameters can evolve together. And of course, the model still needs to fit in the bias memory. But then that's when sharded data parallelism comes in. So you basically say, okay, a GPU A, you have only half of the parameters that you own, and whenever you need to compute whatever you need to compute, and you need the other half, you will ask the other model to give it to you. And so each node keeps a portion of the parameters in memory, gather the weights needed to perform a computation, and then deallocates. And so you can go kind of round robin across the model and only gather whatever it's needed at each time. Of course, this implies a bit more communication, but you can fit larger models in the same GPU. And then we saw modern parallelism. We don't have an out-of-the-box solution for model parallelism right now. There are many solutions out there, but not so many in the end. And so we're watching the space. We are allowing you to do whatever you want with Fabric, so it's really easy. But there's no turnkey pipeline parallelism option in the trainer yet. I'll be happy to take suggestions for what you guys use. I'm very interested in knowing if you use, if any of you is using model parallelism heavily. Of course, we know Megatron, Nemo Megatron uses 3D parallelism, and it uses PyTorch Lightning itself. So it's not that we don't have support for that. It's just that there's no switch on the trainer flag that says, okay, make it pipeline parallel. And in this case, this is the naive way of doing model parallelism. There's a huge bubble of inactivity. So the two GPUs are inactive when one GPU is inactive, while the other is computing. And so more smarter pipeline parallelism schemes use micro batching and interleaving computations so that GPU A can compute a part of the forward on a micro batch, while the other is computing the forward on the other micro batch, and the same is for the backward. And there's always more opportunities for interleaving even more aggressively. And then there's tensor parallelism. There are layers that you can use out there. For example, the FAIRSIC repository has column parallel linear and raw parallel linear that you can use in your models without any problems, where basically each operation is sliced either column-wise or row-wise. And if your operation mesh, then you can compute matrix multiplications in blocks. And you need to be, of course, aware of how these things work so that you can actually use the right operation at the right time. And this is an example of column-wise and row-wise multiplication. But we won't go into that. There's a nice blog post by Sebastian Raschka that explains this really simply. Sebastian is one of our lead AI educators. Okay, so how do you do it in the trainer, for example? You just specify DDP. Yep.
We have a question from the audience, but I'm wondering
Absolutely.
What is the application? So the question is, what if I want to split up the model inside of the GPU?
Inside of GPU, so one single GPU, and you want to split it up. And why do you want to do that?
Jonathan, could you explain why do you want to do that?
Yeah, just to focus the use case a bit more.
Jonathan, you may unmute yourself and talk. He said no use case. He just
oh, okay.
Curious.
Oh, no. That's fine. I think that why you want to split up a model in general, right? You want to achieve, and why you do go distributed. There are two cases. One, you want to increase your batch size and compute faster. And the other one is because your model doesn't fit. So if your model fits, then and your batch size, you can make it large enough. I wouldn't recommend splitting anything up. You could use micro batching to increase the effective batch size. But in the end, if you can keep your model together the most, then you get the most out of your accelerators. Because you will be performing matrix multiplications and operations that are more fused together. But if your model doesn't fit at all, then yeah, you need to take a hit on the GPU utilization by splitting it up. But every time you split it up, you're paying a toll on the GPU utilization. So it's actually better not to split anything up if you can. And then in terms of strategies, we've seen DDP, and then we can go in deep speed, and this is how you specify deep speed. You can also instantiate a deep speed object and pass it to the strategy. And so the trainer or Fabric will actually set up your model with the deep speed strategy and do all the things that are needed to make um, your model and your optimizer and so on compatible. And you can also not use a string, but use a deep speed object where you have more granular control on the settings. But essentially, just to map the space, deep speed is a way to do sharded data parallel, more or less. But what you shard depends on the so-called stage in DDP0. In stage 1, you only shard the optimizer state. You remember there were parameters, gradients, activations, or activation gradients and optimizer state. And the optimizer state was the more chunky. So stage 1 will shard your optimizer state, but the speed. And so the sharding will only come into play when you call optimizer step, which is infrequently. So the speed remains at parity with DDP, but there's a memory improvement. Now, if your model is too large and still doesn't fit, then the next thing you would do is you shard the optimizer state and gradients. This remains at speed parity with DDP, more memory improvement, and this is because the gradients are again synchronized rather infrequently compared to others. There's stage 2 offload, which means you offload the optimizer state and gradients to the CPU instead of sharding across GPUs. Of course, there's some device transfer, so it's not optimal, but of course you can use the main memory to store parts of your model. So there's an improvement there for sure if you just can't fit. And more aggressively, if you go to stage 3, which is, of course, it's not that stage 3 is better. With stage 3, you can fit larger models, but you're paying on communication because at this point you're also sharding parameters, which means if you do a forward on your model, you'll need to gather the parameters that you need to do the forward, and optionally also activations. But of course, you can fit larger larger models, and of course it also depends on how fast your networking stack is underneath your model, so that you may not notice that there's increased communication, practically speaking, or you may a lot if you don't have a optimized networking stack. And the offload is the counterpart. So you offload all these things to the main memory, and here, you will need to transfer back and forth quite a lot. And then there's just activation checkpointing, which is what we covered before, which frees the activations after the forward pass, one every n, so you trade some recomputation for memory. And so this is all very complex, but it's all very simple as well, because you can just switch from one to the other and see the effect of those things without changing your code. This is how you do it. Yeah.
Can I have a question?
Yes.
Yeah, when you go to one slide back about the devices, number of devices. Yeah, this one. So
sorry, here. Yeah.
Yes, there is a device, number of devices, and number of nodes. Could you explain a little bit of the difference of them?
Yeah, for sure. Number of devices is how many devices you have per node, and then how many nodes you have in your cluster, let's say.
So devices basically is the number of GPUs, maybe?
Yeah, sorry, devices is GPUs. Yeah. Okay. It's number of accelerator devices. Yeah.
Okay. Thank you.
Yeah. So we can go. This is the scheme here, essentially. you have 8 GPUs per node, and you have 4 nodes. So you have a total of 32 GPUs.
Yes, thank you.
Okay, and here we saw how to specify the strategy with a string, and here is how you specify the strategy with an object where you have a very fine granular control. You can also specify YAML files or JSON files, I don't remember, that DeepSpeed itself uses for the configuration, where you have extra control on everything. And something you want to know is that if you're using sharding, you want to instantiate the model in the configure sharded model hook, because this will avoid the model. If you do it in init, it will try to load the whole model when you instantiate the module, and this will make your device go out of memory here. While if you do it in configure sharded model, then Lightning will know that it doesn't have to create your whole model in memory, but it will wait until the processors are up, the sharding strategy has been decided, and so it can allocate just the part that pertains to each shard. All right. This is FSDP, which comes with PyTorch. You can use it using just FSDP. It's a sharded DP that shards everything. Of course, it's configurable the same way, and it optionally offloads activation optimizer state. So they're similar technologies. Of course, you can just try out and see what fits your use case better. We have support for others. I just want to mention Colossal because they have had a very nice growth. Again, it's a zero data parallel, which is similar to the approach that DeepSpeed has. But it has, on top of it, it has a dynamic chunk-based memory management, where the placement, it can be automatic and dynamic, so it will kind of optimize as it goes according to the size of the model, the devices you have, and so on. So, but the usage is exactly the same. So you can, as long as you implement your model within configure sharded model, then you can play with all the strategies and see what fits your needs the best. And yeah, more or less, I'm done. I just 2 minutes. If I have, I know I'm out of time, but if I just have 2 minutes, I want to introduce the theme of compilation. Do we have an extra 2 minutes?
Yes, sure. Go ahead.
Okay. Okay, great. All right. So so far we have tried to fit models to execute them in a distributed environment. But what happens when you want to make sure that you're running as fast as possible, even on a single device? So the way PyTorch traditionally runs is that every command, every line of code corresponds to a kernel being executed on the GPU. And the execution is eager in the sense that it starts and ends where you see the lines. It's not in practice. It's not exactly that because it's asynchronous, but essentially the framework doesn't have a notion of the fact that after a matrix multiply, you will have a mass fill, and after the mass fill, you will have a softmax. That has no visibility in it. So it tries to make each and every operation as fast as possible in its own self, but it won't be bothered by what happens after. So this means that it will fetch the data from not from main memory, from device memory, from GPU memory, in the compute kernels, take the result, put it back in memory, and then the next operation needs to be executed, and this dance will happen again, which is fine for the most part, except that on modern hardware, this is becoming a bottleneck. And this wasn't a bottleneck a few years ago. So the way the tensor cores ran and the way the memory bus between the tensor core and the memory on the device were laid out was quite balanced. But lately, compute has gotten a lot faster, and the data fetch has become faster, but not by the same amount. And so, the more time you spend in compute, the better it is. And the less time you spend going back and forth between compute and memory, the better it is. So in the end, it would be much better if I knew that after matrix multiply, I have a mask field and a softmax so that I can execute them all at once without moving data, and then the result I move back to memory. And this is why Torch compile and other compilation technologies that are landing today are important, because instead of executing one command at a time, you acquire the program. You generate an intermediate representation of the whole program or the chunk of the program. And then you try to fuse and optimize all the operations that the program has so that you can execute them as an individual code block, kernel block on the device. And so you get uninterrupted computation and your GPU utilization goes up. Otherwise, you will starve your compute. And so what PyTorch 2 does, it takes some code, it starts to run it, and then there's this technology called Dynamo that will analyze your code as it's running and acquire it. Essentially, it's looking at Python bytecode. It does some optimizations. It passes it to an executor, which is called Inductor, which provides optimized kernels, fused kernels, and it's based on OpenAI Triton. And DDP is already supported. FSDP is getting there right now. And so the good news is that we have full support for PyTorch 2 and torch.compile here. So basically with Lightning, you can instantiate a Lightning module, run torch compile on the Lightning module itself, and pass it to trainer fit, and the execution will be sped up by Dynamo Inductor transparently. All right, so this is what I wanted to cover, and this is our assets, and you're free to come on our Slack. We also have a Discord right now that I didn't mention here, but if you're into Discord, you can join the Lightning AI Discord, and we're very active there. And we have new stuff coming down the pipe, so we'll be happy to chat and interact with the community.
Thank you, Luca. And now we know how Lightning AI can help us to scale our models and how easy it is to use. Are there any questions from the audience? We have asked a few questions already. Then again, thank you, Luca, for the wonderful presentation.
Thank you.
Thank you.
Thank you very much. Thanks for having me. Bye-bye.
Good day. Yeah, bye-bye. Thank you.